Hi everyone, welcome to Fig Tech Talks. I'm your host Stuart Campbell, the Principal Consultant at Fig Technology Solutions. In this video, we're going to take a look at a great tool for managing infrastructure as code, Hashicorp's Terraform. We'll talk a little bit about what it is, why you might want to use it, and do a demo of it in action. Let's jump in. So, what is Terraform? Terraform is the declarative tool, which means it's a tool where we define an outcome, not a specification for how to achieve an outcome, for building and managing infrastructure in lots of different places. It's an open source tool primarily developed by Hashicorp, and as is usually the case with OSS today, you can also get it with a sprinkling of enterprise support if that's what your company needs. First, let's look at what it does. So as I mentioned, Terraform is a declarative tool for building and managing infrastructure as code. For those of you that are familiar with infrastructure as code, forgive a brief diversion, but for those not familiar, the concept is that you manage your infrastructure into what is now referred to as a GitOps model. This means that you use the patterns and conventions of software development, things like code reviews, pull requests, to help manage the infrastructure your code runs on, not just the code itself. If you're familiar with tools like Azure Resource Manager templates and AWS CloudFormation, think this, but with the ability to develop across multiple different types of infrastructure and across multiple different cloud providers. As of recording, there are around 140 official or verified Terraform providers and another 683 community provided ones, meaning that you're almost certain to be able to find something that you can code with Terraform. You can check out the full link at the Terraform website, registry.terraform.io. This to me is one of the big benefits of Terraform. It isn't locked to a single platform like ARM or CloudFormation, but you can learn the skills and the language of Terraform and then apply those concepts across multiple cloud providers. This isn't a case where you can write once and deploy anywhere. It's more a case of you can learn Terraform and the skills needed to manage and deploy infrastructure using Terraform, and you don't have to worry necessarily about what cloud provider those skills are applied to. Now, of course, there'll be situations where, Microsoft do something specifically and AWS do something a little bit different, and you have to manage those use cases. But as a general rule, you can learn Terraform and then apply that to those cloud providers rather than having to learn ARM and CloudFormation separately. So if you're thinking about running a multi-cloud strategy or a hybrid cloud where you run on-prem and in a specific provider, then you can use Terraform to abstract those platforms away and give your infrastructure team one place to manage their code. The other big benefit is the ability to consistently reproduce your infrastructure across environments. Now you don't need to worry if staging is exactly the same as production. If you source them from the same Terraform code, then you can know that they are. In a previous role, I used Terraform and Ansible, which I'm going to cover in a future video, to define, build, and maintain 3 separate environments, so a development, a QA, and a prod. And they were deployed across 9 data centers on a niche cloud provider, which didn't have anything to the level of ARM or CloudFormation. I could spin those environments up and down in a matter of minutes and be confident that the app platform would be ready to go once Terraform had finished running. So there's a lot more to discuss, but let's head over to a demo and see it in action. Okay, so the first thing we're going to do is make sure that we have the latest version of Terraform running. I'm running on macOS, so I'm going to use Homebrew to manage my module installation, but you can go to the Terraform website and check out the docs for your platform of choice. So the first thing we're going to do, I'm going to get the Hashicorp tap, make sure I'm spelling things correctly. And just hang out here whilst it updates. And then we're going to install Terraform. So brew, install Hashicorp Terraform /tap. Oops, okay. Got those around the wrong way. There we go. Once I got it spelled right, it's going to work properly. So now we're going to get that from Homebrew. That might take a few minutes, so we'll come back when it's done. Okay, now we're back, and we can check that Terraform's been installed correctly by running the terraform-version command. And there we go. We can see we've got version 15.1 installed on my Mac. So now that we have Terraform up and going, we need to make a new project. So let's make a new directory. Let's jump in there. And let's open this up in VS Code. Okay. So in this top level project folder, we're going to have two child directories, modules and environments. The reason for this is that we're going to build a module that defines our environment and any submodules that might make up components of that environment, and then implement that module repeatedly across different environments. You can think of a module in Terraform a bit like an NPM package. You can define one or more elements of your infrastructure and reuse them across different implementations. Modules can be imported via Git, so these become a really powerful way for, say, your server team to define a standard set of servers that everyone can use, and then have project teams just import the server that they want for their specific project that meets their specific needs. Today, I'm just going to be importing from the local directory, but all the same concepts apply, no matter where you import the modules from. So let's create those two directories. We've got modules and environments. And let's just jump in and start with our core module. So whenever you build the Terraform module, the recommendation is to have four main files: main.tf, variables.tf, outputs.tf, and readme.md. We're going to take a shortcut today, not document as well as we should for a production system. So we're just going to end up using two files, main.tf and outputs.tf. So let's create those now. All right. Now, when we're developing our core module, we need to define what's called a provider. In Terraform, the provider is the interface between the Terraform and the TCL, the Terraform configuration language, which is what we write in Terraform, and our cloud provider, which today is going to be AWS. Normally for a module, we would rely on the fact that a module inherits the provider implementation of its parent, but simply, since we haven't written the parent yet, for now, we'll just define it here. Let's open up our main TF, which we've got on our VS Code window, and put in the code to define the provider we want to use. It'll start with Terraform and define the provider we want. So let's jump in here. And there we go. So now we can see we've got a Terraform, required providers, and we're going to use AWS. We're going to source it from the default Hashicorp AWS provider, and it's going to be a version greater than 3.0. So once we've got the required provider set up, we need to actually define the provider itself. So let's go ahead and do that now. So we're going to define an AWS provider. We're going to set a region, which in my case is going to be AP Southeast 2. That's the environment that happens to be closest to where I am. And a profile, which is the AWS CLI profile that Terraform's going to use to go and connect and deploy these resources. So once we've got our provider, we're also going to need a VPC to store all our Amazon resources in. So we go ahead and create an AWS VPC called Terraform Demo, and we're going to give it a CIDR block, just a straight 10.0.0.0/16. So as I said, to define anything in Terraform, we need to write in the Terraform configuration language, or TCL. This is, as the name suggests, a Terraform-specific language. TCL is declarative, again, means that we specify an outcome, not how we want to achieve the outcome. It boils down to a few basic elements. Blocks, which are containers for content, usually the configuration of a specific resource like a VPC or a server. Arguments to assign values to attributes within a block. Expressions, which either represent a value literally or as the result of combining other values or the result of internal functions. And this is a real power point in Terraform, is this ability to use expressions and variables and internal functions makes your infrastructure code really, really powerful and really, really reusable. So let's use our VPC as an example to break this down. So the resource is our block type. So what sort of Terraform block this is. This is almost always going to be either a resource or a module, but you can see we've already run into a couple of outliers, provider and Terraform. AWS VPC is our first block label. The convention in Terraform is that this is telling the provider, in our case AWS, what sort of resource we're going to configure. And Terraform demo is our second block label, which is telling Terraform what the unique name of this resource is going to be. If we need to refer to this component later, we'll do so using the two block labels that are defined here. And lastly, our argument, which is cider_block, and that's dependent on the resource, dependent on the block. You can pass in attributes and set the values of those attributes, and this is what's going to end up being configured by the provider on the infrastructure layer. So let's go a little further. Sure, we could hard code a bunch of values into our code, but that's not very reusable and not very helpful necessarily. So how do we introduce variables to manage this? Well, just like anything in Terraform, we can define a variable as a block. We give the variable name as block label number 1, and we can define its type, its description, and a default value to be used if nothing is set. So let's add 3 variables to our code now. So we're going to add a variable AWS region, base CIDR block, and AWS profile name. So you can see, let's look at AWS region. So there's our variable block, and then block label 1 is our variable name. It's going to be of type string, and it's going to be, going to have a description, the name of the AWS region in which to deploy the resources. Pretty straightforward. Let's look at the base CIDR block. So you can see we can also set default values. So if this value for some reason isn't set by the person calling our module, we can use this value as our default. And we can then reference those variables in our code using the var.blockLabel1 name convention. So let's replace our code here with some code that uses those variables. And here we see, so region is now set to var.awsRegion. And you can see it links to our variable up there. So now we can dynamically set these values. Now this means that people aren't confined to the region that we initially defined. The structure is the same, but the location or the region is going to be different depending on what values you pass in. So let's now finish off our networking configuration. We're going to set a bunch of subnets for each availability zone in a specific region. So you might be thinking, well, how do we do that, Stuart? AWS regions all have different availability zones depending on how many data centers they have. So luckily for us, a Terraform provider isn't a one-way street. Not only can we put data in the system, we can also pull it out. We do this by using a special kind of block called a data block. Let's do one now, which looks up all the available availability zones in our region. So we can see here, we've got data, block label 1, AWS availability zones. So we're telling the provider, get us the information about availability zones. We're going to give it a name of available, and then we're basically going to filter that result by state equals available. Now we can go ahead and create a subnet for each of those availability zones. So again, we've got our resource block, AWS subnet, and the name of AZ subnet. And now we're going to make use of some of the really cool inbuilt functions of Terraform. The first is a special argument called count. Count essentially acts as a for loop going, we'll create a resource of this type for however many we put into the count. In this case, we're going to say create a subnet for the length of the data availability zones.available.names. Basically, we're going to count the result of this data block and create an AZ for the length of the array. In the availability zone, we're going to set the number, we're going to set the zone to be the index of this array. So it's going to loop through the array and set the subnet zone to whatever the index of the loop we're in. We're going to assign it to our VPC ID. And here's our first example of referencing an existing resource. So you can see we've got our block label 1, AWS_VPC, and our block label 2, Terraform_demo. And then we've got our ID attribute. And then lastly, we've got a really cool IP addressing function, and there's a couple of these in Terraform. I definitely encourage you guys to get in the docs and take a look. We're going to use this CIDR subnet function from our base CIDR block that we set on the VPC, we're going to create a /20 address space for each of these subnets. Now, because we also probably want to keep most of our subnets private, we're going to create another subnet, which we'll make public, and then we're going to add all the necessary AWS infrastructure, NAT gateways, internet gateways, routing tables, etc. And we're going to set all that up so that our machines can talk to the internet, but the internet can't talk to our machines. So let's just go ahead and dump all that in now. So what you'll notice that's interesting about this code is obviously there's a bunch of new resources, but the most interesting block is this new one called locals. Locals is a special type of variable that's scoped to the file in which it's declared. So this variable here, private subnet IDs, is only available in this file. In this example, I've taken the ID attribute for each of our private subnets using what's referred to as the splat format and assigned it to a list, private subnet IDs. So the splat format is this lovely little dot star dot in the code here. And what this does is it iterates over a collection and creates a list of a specific attribute from that collection. So with this splat formatting, I'm saying for every subnet in AWS subnet AZ subnet, which you'll remember we've created as many of those as we have availability zones in our region, get me the ID attribute and add it to this list. And this then means we can take that list and again, using count and our length function, we can create route table associations saying for each of the private subnets, here they are, subnet IDs, local private subnet IDs, count.index, and associate them to the private subnet route table. And you can see up above here, we've added the route. So we go, all internet traffic goes out via our NAT gateway. And that's how you can use local variables and loops to create associations in multiple different, between multiple different resources, and flexibly as well, because it will only create the number of associations as we have subnets to create them to. We also want to create a new security group for our management hosts. So what we're going to have is a jump host in our public subnet that we can SSH to, and then we can SSH from there into our hosts. So we'll first jump in and define our security groups. So here's our new security group, letting us get SSH access from everywhere and letting us access the internet. And we also need to add an SSH key. There are some really cool internal resources in Terraform that let us do that. So we're going to create a new TLS private key, RSA algorithm for 96 bits, and then we're going to assign that key to a new AWS key pair. So at this point, we've got the basics of our AWS network. So let's look at creating a submodule to define our compute environment. We'll start by setting up our module like we did earlier with a new folder, a main.tf and an outputs.tf file. And we'll skip the variables.tf file because these variables will always be set by calling the module. So let's jump in. Let's make a new directory, compute_stack. Let's jump into that directory. Okay, let's open up our main.tf and we can start defining our stack. First thing we're going to do is we'll add a new variable called label, And this will let us pass in a prefix to any of the names we want to give our resources later. So let's work on defining our resources, and we'll add in a bunch of variables that'll let us customize those resources as we go. So as we saw in the main module, data is not a one-way street between the providers and our code. So what we're going to do is we're going to use a new data block. And this time we're going to get from the list of AMIs, we're going to call it Ubuntu because we're going to end up pulling an Ubuntu AMI. We're going to get the most recent result that matches our criteria. So where the name filter is this specific name, so an Ubuntu server, and it's an HVM virtualization type, and it's owned by the canonical AMI owner ID. So we only get an official Ubuntu image. We're going to use the result of that value later when we define our auto-scaling VMs. So we also need to control who and what has access to these VMs inside our auto-scaling group. So the goal here is to let every VM in the group access the internet, allow only our management hosts to SSH into the server, and allow only network traffic from our internal load balancers and limit it to a specific port. So this is going to be quite a few new resources, so apologies if I go a bit too fast here. So let's start by adding a couple of new variables. So the first one here is our management security group ID and our ingress ports. So what's the ID of the management security group so we can permit access from it, and what ports do we want to allow into our auto-scaling group. This is the basis for the security group for our VMs, but we also need one more thing, which is the ID of the VPC where these resources are going to live. So we've got that now with our new variable. Let's set up our security group and our security group rules. So we start with our security group. There it is. You can see this is an instance where we're using our label. So we're saying, we're going to give it whatever the value of var.label is, _security_group. And even in the description, we're going to use our label to help us later figure out what all of this stuff is for. In another example lower, I've got an example where you can see us using tags to achieve a similar result. So we've got our security group rules, which is saying, the egress rule, letting everyone access the internet as much as they like. And we're going to say you can only SSH from our var.management_sg ID. So that's where that variable is coming in. We then want to do a security group for our load balancer. So in order to set up our load balancer, we first need to have the IP range of the VPC. So basically, we want anyone inside our network to be able to hit our load balancers. So let's start by defining that. And then let's build out our new security group for our load balancer. So this is making use of another inbuilt function from Terraform, so another special argument, just like count. We can also have a for each. So where for was more of a, for I, I increment do blah kind of loop, this is more of a for each loop or a map, on an array. So for each of the values in our var ingress ports set, we're going to set a rule of type ingress, and we're going to say from port, so each key, so for each key in the ingress ports set, which is going to be our port that we want to allow access to, and we're going to set up the rules so that everyone in the VPC is allowed to hit that port on the load balancer. We're going to repeat that process to allow the same things from our load balancer to our compute resources. So there'll be the compute ingress, and we're going to, again, for each ingress port, we might actually change these so that they are a bit better. And then we will allow access to and from there from our LB group to our compute security group. So now that all the security groups are set up, we can build out our load balancer. The first thing we want to do is add yet another variable for our subnet IDs. So the load balancer needs to know what subnet IDs it's going to load balance resources across, so it can have its networking and routing set up. And then we're going to build out the load balancer. So we can see here again, here's our resource block, our block label 1 and block label 2. It's going to be an internal load balancer. We're going to set that to true. We're going to assign it our LB security group that we built before. And we're going to use a new type of block called a dynamic block. So a dynamic block, again, is another variation on the for looping that we've been doing so far. But this is basically saying that we're going to repeat this listener block as many times as there is content. And this is really useful for some provider resources that allow you to define multiple blocks to set up things like load balancer ingress rules. So we're going to create a dynamic block for each of our var ingress ports. And this is what the content's going to look like. We're going to have an instance port that is our listener key. And then we're going to have a protocol TCP, and then we're going to have a load balancer port, which is, again, that same value. So that's going to say, for our load balancer, for each of the ingress ports, set the incoming and outgoing ports to the same thing on our load balancer. So basically, anything that hits the load balancer, we're going to forward directly to the servers on the same port. Now, after all of that, we can use this to build our launch instance template for our instances. So we're going to need to be allowed to access our servers. So let's create our variable for our SSH key so we can set up which AWS key is allowed to access these servers. And then let's build out our launch template. And so in our launch template, we're making use of our AMI ID. So we're going to set the image ID attribute to be the value of the Ubuntu AMI we looked up earlier. And then finally, we're going to create our autoscale group. And in order to do that in the most flexible way possible, we're going to add 3 more variables. Desired capacity, max size, and min size. So that's just telling our autoscale group, desired size, how big and how small it's allowed to be. And then last but not least, the actual autoscale group itself. And we actually need to fix this up. Should be $default. There we go. So that defines our compute module. So we can now go back to our parent, our environment module, and define and make use of our new module there. So let's go back up to our top level module. And we do that by using a new block type, the module block type. So let's put the code in here. And so we can see our block type is module and label 1 is front end compute. So we're going to source this module locally from compute_stack, which is the module we just finished creating. Again, you can source these in a number of different ways. I encourage you to read the docs if you're after more information. I've done it previously from Git and it was fantastic. We're going to give every resource in this module the label of front-end. We're going to pass in our management security group ID. We're going to pass in just the one ingress port. So these are our front-end servers. We're going to pass in port 80. Obviously, you wouldn't use port 80 for a web resource in this day and age, but just to provide a bit of demonstration, a bit of context, we're going to pass in the VPC ID of our VPC that we create, the same CIDR block that we've passed in previously, all of our subnet IDs, and for the sizing of our autoscale group, we're again going to use our length function. So based on the number of AZs, we're going to say, desired capacity is 1 VM per AZ, the max size is 2 VMs per AZ, and then the minimum size is 1 VM per AZ. And of course, our SSH key name so that we can access those servers later. Now, the whole point of the modules is obviously that it makes it easy for us to reproduce this infrastructure again for different types of resources. So rather than just front-end resources, we can also use it for back-end resources. So again, we're sourcing from the same module, but this time we're going to use back-end instead of front-end as our label, and we're going to assume we're running something like RabbitMQ, and we're going to have port 5672 as our ingress port. So that is our compute stack. We're going to create one more module now for our management host. So let's jump back to there. Let's create our management module. So we're going to call it management underscore hosts. We're going to change down into that directory. And again, we're just going to have our main.tf and our outputs.tf file. And let's jump in there in VS Code. And we'll set up that file for our management module. Bang, there we go. Now, for our management host, it's not enough just to set it up. We also need to know, well, what IP is it? How do we access it? So inside our module, we defined an elastic IP, a public IP in AWS for our management host. And now we're going to use our outputs files to get access to that information from our command line. So we're going to define a new block type, which is called the output block type. So you can see we've got an output, block type is output, block label 1 is public IP, and we're going to set the value of that output to be the management host's public IP address. So from there, we can now go back to our environment module, our parent module. We can set up the management host. We can pass in the variables that it needs. But this is really critical, it's really important to remember, is that just because you've output something from a child module does not mean that that will be available at the top level module where you might be implementing the resource. So you have to output information that you want at the top level, every level up as you go. So for our management IP address, we've output it from our management host module, but now we also need to output it from our parent module, and eventually we'll have to output it from our environment as well. But for now, let's jump into the outputs of our environment, of our parent module, and let's get those outputs going. There's also a couple of other outputs that we need, which is our private and public key details. And we'll talk a little bit more about the security of those in a sec. Now, these aren't the only outputs that we need. We also might want to know, well, we've got some load balancers set up. How do we hit those load balancers? How do we know that we've got access to anything on the other end? Well, again, we can jump back down into our compute stack, into outputs.tf, and we can add some outputs for those files. And again, just because we've done them at the child doesn't mean they're available straight away from the parent. So we have to go back into our parent and add in a few more with our DNS names. And so now everything is defined in our environment and we should be able to build it out. So we can jump back up, environments. We're going to make a new environment. It's going to be called development. Jump in there and we'll create our two main files. This time, instead of calling it main, I'm just going to call it development so that it's a bit easier to reference, and outputs.tf. Okay, so in VS Code, let's jump into those. And then we can implement our main module. And there we go. It's that simple. So all of that infrastructure, all of that information, all of those details that a developer isn't necessarily going to understand, or you may not want your developers to understand and have access to, can be completely abstracted away. That parent module that we built with all of the infrastructure details in it can be completely managed by a different team. And all the programmers, all the developers need to know is what values they should pass in and where they need to source that module from. This means that the developers can build out consistent, repeatable infrastructure without having to know any details about what is underneath. And this is the whole benefit of something like Terraform or infrastructure as code in general, is that you don't want your developers to necessarily have to think about this stuff. But it is important, it's critical that your operations are manageable, scalable, and repeatable. But you're never going to get that unless you have centralized control, which is why something like Terraform and its module system is really, really powerful. So we've got our environment set up. We also need to set up our outputs, because remember, we're not going to get those unless we configure them at the level we're working at. So let's add these ones in. And now, once that's done, we can start up our deployment. So let's close that out. Let's go back to our command line. And so the first command you're going to want to run is terraform init. So this is an initialization command for Terraform. So what it does, it will pull down any modules that it needs from remote sources. It will pull down the latest version of the provider and store it all within its self-contained folder. So let's just run that. Hopefully it works okay. Shouldn't take too long. There we go. Terraform's been successfully initialized. Let's just clear our screen. And once that's completed, you can see over in VS Code, we've got a .terraform directory, and it's got all of its modules. It's got a lock file, and it's got its providers. So the next step is to do a dry run of our deployment so we can check our work and make sure we're actually building what we think we are. This step is critical both initially when you first build an environment, and especially once your environment is in place, so that you are reviewing and understanding what changes are going to happen to your environment. The ideal setup would be that a developer makes a change to one of the underlying modules. That developer then pushes those changes in a pull request that has the plan attached. That plan is then reviewed by somebody else in the team, approved, merged, and automatically deployed. Now, that's obviously a level of maturity that very few teams may reach, but that's the ideal scenario. So we're going to just do it all manually here. We're going to do a Terraform plan. We're going to use the -out command to create an output, and we're going to call it development.plan. So now our plan's going to run. It's going to connect with the provider. It's going to check the state of the infrastructure versus what it thinks the state should be, and it's going to produce a plan, a declarative plan for how to make the infrastructure look like our code. Oh, okay, so we can see an error here. So this is the point of security that I wanted to make earlier. So it's saying that this SSH private key seems like it could be sensitive information, and we should really mark it as such. So let's go back to our outputs, and let's add that command, sensitive equals true. And then let's run our plan again. And there we go. I won't run through the complete details to the plan, but you can see here that there's 37 resources to add, 0 to change, 0 to destroy, and it's got some changes to our outputs. It's also, helpfully, given us the command we can run to apply this plan. So I'm going to execute this command. We'll hang out for a couple of minutes while it runs, and I'll be back to show you a bit more about the environment. Okay, and we're back. So our Terraform's finished running. As you can see, we've got some outputs here. So we've got our backend load balancer name, our front-end load balancer name, the public IP address of our management host. And critically, you can see here the private key has been marked as sensitive information. So that information won't come out during the command line run of the tool. You can only get that information if you have access to the state file, in which case you can then run some local CLI tools to extract that information. This is really critical. It also touches on correct state file management, which I'm not going to cover in this video, but is absolutely critical for securing and managing your Terraform environment safely, particularly in a distributed team. But we won't touch on that today because it's a little bit more complicated than I'd like to get into right now. But you can see that it's protected, so it won't come out during a CLI run, which means that if you're using, GitHub Actions, GitLab runners, etc., any CI/CD tools to deploy your infrastructure for you, that information isn't getting logged and it's not available for people to jump in and see. So you can see, 37 resources added, 0 changed, 0 destroyed. So now let's test it out. So I'm going to grab, hopefully I'm going to grab the private keys. No, that's not it. So using the command line tools, I'm going to grab the private key, and we're going to output that to an SSH key so that I can access it later. We're going to do the same with the public key. Make sure those keys have the correct permissions so that SSH doesn't have a sook. And then we're going to connect to our management host. So we're going to use our Ubuntu user and our management host. We're going to use the key that we've provided. And there you go. You can see we're logged into our server there. We're on our Ubuntu server. There it is, looking nice and pretty. But we also want to be able to access, the autoscale VMs, the ones that are hidden in our private subnets. So I'm just going to do a bit of work here to get the SSH keys onto our server just by a bit of cutting and pasting. And then I'll add them here. And then we should be able to jump to one of our autoscale VMs. So I'll just have to log into the console here and get an IP address of one of those VMs. I've got one of the IP addresses here. And there you have it. A working implementation of dynamic autoscaling groups across multiple availability zones with Terraform. Now, I'm going to put all this code up onto GitHub, so I really do encourage you to pull it down and try it out yourselves. And of course, if you've got any corrections or updates or changes you'd like, shoot me a pull request and I'll be happy to sort those out for you. I really want to reiterate that Terraform isn't a tool that lets you run once, write once, and deploy everywhere. Its real value is in being able to learn one language, one way of defining infrastructure, and then learning to apply those tools to the different cloud providers. I find it really helpful. I think it's a fantastic tool. Like I said previously in the video, I used it in production. It was amazing. I really can't speak highly enough of it. And that's going to wrap up the video for this week. I hope you really enjoyed learning about Terraform. I had a lot of fun going through it for you. If the video has been interesting, if you like any of the videos I work on in future, please be sure to like and subscribe to the channel. Until next time, thanks for watching.